So welcome to your very first online lecture in Edpuzzle. A couple things about Edpuzzle. It gives me superpowers. You can't fast forward through this, so don't even try. Our online lecture today hopefully will be under 30 minutes, and it is on metathesis, which is really better known as double replacement. We're going to go over the basics, practice a few, and learn a little bit about solubility as well. So a few of the basic ideas that we need to go over for metathesis. Number one, it's an exchange of the anions. And remember, anions, oh my, this is not good. The anions are the negative part on our compounds. And we also have to have a driving force. And if you remember, we had talked about those driving forces before when we were doing our aluminum and copper 2 chloride lab. That was one of our pre-lab questions we had. Well, specifically with metathesis or double replacement reactions, we're looking for a precipitate, a PPT. We need to find the solid. And if we can find a solid that has formed, then we know that it is a reaction has occurred. Another potential is to look to see if a gas has formed, and there are several gases in particular that we are looking for: hydrogen sulfide, carbon dioxide, sulfur dioxide, and ammonia. Ammonia. That was wrong. Last thing, now this one's a little bit harder because it's not obvious. A solid, you see it form, that's obvious. Gas forms, there's bubbles. This one, you really need to look at the balanced equation in order to know whether this has happened, whether you have formed a molecular species. Our most famous molecular species, of course, is water. We also have what are known as weak species or non-electrolytes, and we'll talk more about those in just a little bit. This one you definitely would have to look at the equation for, because you're not going to know if water forms or not. That's not going to be obvious. So a little bit about understanding solubility. What does it mean to be soluble? Solubility refers to the ability of an ionic compound to dissolve in water. And if you remember, we more commonly refer to those as aqueous solutions, gave them an AQ. The more soluble something is, means the more it dissolves. And in fact, last year we even looked at solubility charts that would show in 100 milliliters of water how much table salt or potassium nitrate we could dissolve. There is no such thing as something being completely insoluble, meaning something is definitely always a solid. It never does any dissolving whatsoever. Solubility is relative. We really need to talk about not whether it's soluble or insoluble. Sometimes it's talking about the degree of solubility. This compound is more soluble than the other compound that we are looking at. How we get through this process of dissolving at a particle level. When our ionic solid dissolves in water, it breaks apart into single ions, which then become surrounded by water molecules. I want to make sure you make a note right now that you need to ask me about this tomorrow when you see me in class, that you want to see the water molecules and the table salt. And we can actually visualize. I have manipulatives that you can use to actually see how this process occurs. Kind of to better understand, why do salts dissolve, why do ionic compounds or salts dissolve, is we need to know, how do those solids hold together? What's in there? A lot of years, last year, if you had me, we talked about the electrostatic attraction that was present. That just means the positive is attracting the negative. Another way to talk about that is Coulomb's law. Coulomb's law, you can see on this slide, we have the force of attraction is equal to a proportionality constant times the charge on the positive ion times the charge on the negative ion divided by the distance between the ions. You don't ever have to use this calculation. You may see it on the AP exam, but they would never ask you to calculate it. What we do want to see is how does charge play a role in whether something dissolves or not. So here on the left, we have this first purple cation, which is +1, and the green one, which is -1, and we want to do comparison 1. Is the force of attraction stronger or weaker here? Well, one of the things that plays a role is the distance between the charges if you think about a number line. Is the distance between the charges in our +2 -1 greater than or less than our +1 -1? Well, it has a greater difference. Because there is a greater difference in the charge, bigger charge differences mean stronger ionic bonds. So in this first comparison, in comparison number 1, really our second compound that we're looking at, it should be less soluble than the original +1 -1 sample that we were looking at. Bigger charge difference leads to a stronger attraction between the cations, meaning that substance is more likely to be insoluble, more likely to be a solid. Now, in comparison 2, we have to be a little bit careful. In comparison 2, notice that the charges are all the same. So charge difference here isn't making, we can't look at that. There is no charge. The charge difference is identical from our original sample to our comparison 2 sample. So now we have to look at the R, the distance in between the ions. And if you notice in our new comparison, the number 1 that has that is bespeckled, notice that that radius is slightly bigger, slightly longer than our original radius. Well, what does it mean if that radius is further apart? That means the nucleus of our +1 isn't having as great of attraction on the nucleus, on the electrons of our -1, and the nucleus of our -1 isn't as able to attract as well the electrons of our +1. So because there's a greater distance between the two ions, this means that this particular compound would actually be more soluble. It would be easier for water to hydrate, come in between that +1 and that -1. So just to review our first sample, now this is probably going to mess up, but I think we'll be okay, is less soluble. And our second sample is more soluble, and I don't know exactly what's going on with the pins. So let's continue on and just kind of do a little bit of a review. Just the basics. The force of attraction between oppositely charged ions is proportional to the magnitude of those charges of the ions. That's once again to the bigger the charge difference, the stronger the attraction will be, the less likely it'll be to be soluble. How we dissolve is during dissociation, oppositely charged ions in the solid phase are separated from each other and dissolved in the water. We know that water has partial positives and partial negatives on it. And what happens is those partial charges interact with the full charges over on, for example, table salt, and it's able to hydrate it and pull the ions apart. So all of this suggests that if a salt is composed of highly charged ions, it's not very soluble. If a salt is composed of ions with lower charges, meaning less charge difference, it's probably soluble. And as a general rule, kind of a place for you to start, any salt involving a +1 cation or a -1 anion is likely to be soluble because that's our smallest charge that we can have. So this likely we're not going to have that great of a charge difference. So on to our next slide. This leads to the idea of using charges to determine solubility. The smaller the charge difference, the more likely the substance will be soluble because the attraction of the ions can be overcome by the hydrogen bonding of the water molecules. For example, in sodium nitrate, sodium's +1, nitrate's -1. This is a smaller charge difference compared to barium sulfate, where we have +2 and -2. Once again, the smaller the charge difference, the more likely to be soluble. Well, this is why sodium nitrate is aqueous and barium sulfate is a solid. Now, I want you to try this one. I'm going to add a question into Edpuzzle, so you should be pausing here to answer your question in Edpuzzle, and we can also go over it in class the next time I see you. Now, one of our trickiest parts is we have all these gases that form. We have hydrogen sulfide, our first gas up there at the top. Please make a note that this one is known to smell like rotten eggs. And you'll know that hydrogen sulfide is formed anytime you take a compound that has sulfide as its anion and you put it with any acid. This will always give us that hydrogen sulfide gas, which smells like rotten eggs, and a salt. Now, when I use the word salt here, I'm talking about just any ionic compound, anything that's got a cation and an anion put together. Next up, we have carbon dioxide. Carbon dioxide doesn't have any real notable odor to it. But what's kind of unique in this case, you'll notice I have two arrows in here. The reactants will be any carbonate compound plus an acid. And you notice in blue here I have carbonic acid. Carbonic acid doesn't stay together very well. And as soon as carbonic acid forms, it actually goes through another reaction and decomposes. And it decomposes into carbon dioxide, water, and notice again we got that salt out there on the end. You need to memorize that when carbonic acid forms, it immediately goes into carbon dioxide and water. You'll see the same thing happening with our sulfur dioxide and our ammonia. For sulfur dioxide, we need any sulfite compound plus an acid, and this makes sulfurous acid. So sulfurous acid is much like carbonic acid. It just doesn't hang around very long. It decomposes immediately. In this case, it goes into sulfur dioxide, water, and then that's salt again, that ionic compound. Also, no real odor associated with this sulfur dioxide. Lastly, we have ammonia. This is any ammonium salt plus a strong base, and just very shortly we'll talk about what those strong bases are. This produces ammonium hydroxide. Ammonium hydroxide is like the previous two, the sulfurous acid and the carbonic acid. It just doesn't, it's not very stable. It doesn't stay together. So it immediately decomposes into ammonia, water, and then once again we have that salt, that ionic compound. we're going to pause here just for a second. Okay, and we're back. My board's back and working again. All of these things that I have put up here in blue, you got to memorize these. These are things that form but immediately decompose into gas and a water. You just have to know these. You don't ever want to write these acids, the carbonic acid, the sulfurous acid, or the ammonium hydroxide. You would never write those on a test paper because they don't exist. So we talked about, did a little bit of practice of, can we figure out if it's a solid or not? What do we need to look for? Then we did a little bit with gases. And the last thing we need to talk about are those molecular species. The following things are not molecular species, but you may often see them form. If they form, it's not a reaction. Nothing has happened. The first one is the strong acids. And strong acids always ionize. They always break apart. You have to memorize these, and you should have them memorized for the very next time that you see me. The strong acids are perchloric acid, chloric acid, hydrochloric, hydrobromic, hydroiodic, nitric acid, and sulfuric acid. These are all strong acids. They are not molecular. They are ionic. We also, if we have strong acids, we also have strong bases. The strong bases always dissociate as well as the strong acids. Notice acids ionize, bases dissociate. Both of those words mean break apart. For this, you need your periodic table. You want to make sure that you recognize these as the group 1 elements. So sodium hydroxide, lithium hydroxide, potassium hydroxide, those are all examples of strong bases, as well as barium, strontium, and calcium. So barium hydroxide, strontium hydroxide, and calcium hydroxide are also strong as well. This is another one of those things you've got to get them memorized. You have to know it. And then the soluble salts, they aren't molecular species either. They dissociate into ions. That goes back to that thing, the things that were on the previous slides about solubility and looking at charge difference and atomic ionic radius in order to determine. So if these are not molecular species, what are molecular species? And the following are molecular species. This means if they form, a reaction occurs. We have weak acids, weak bases, and water. Well, how do I know if it's a weak acid? How do I know if it's a weak base? Better not ask me to know how if it's water or not. For weak acids and weak bases, if they're not strong, then they are weak. So you see there are very few strong acids and there are very few strong bases. So if they're not one of those that we looked at on the last slide, then that automatically makes it weak. Probably the most common ones you run across are hydrofluoric acid and acetic acid. Those are really good molecular species for weak acids. These things don't break apart, so we'll talk about what that means a little bit later on. Really good way to get water to form, if you remember from last year in your double replacement, is a neutralization reaction. Because water was formed, that meant a reaction has taken place. Now we know that that's known as a molecular species, and that's one of the indicators or driving forces for a double replacement. Now, there are 2 more slides, but since my board is acting a little bit strange today when I'm writing on it with pen, we are going to hold off on those last 2 slides, bring your PowerPoints to class, and I will actually do those examples, or Mr. Long will do those examples in class.